Alright, good morning class. This time we shall solve problem involving enthalpy. Alright, so by enthalpy we mean the quantity of heat flow. So it is denoted by H. However, the change in enthalpy denoted by delta H is what is actually being measured. Okay, so the enthalpy of a reaction, delta H, is simply H products minus H reactants. Okay, so this is just a difference between enthalpy of products and enthalpy of reactants. Okay, so the change in enthalpy could be positive or negative depending on the type of reaction. So an exothermic reaction has a negative delta H, whereas an endothermic reaction has a positive delta H. Okay. So a thermochemical equation is one that shows both the mass and enthalpy relationships between products and reactants. So we have here two examples. The decomposition of ammonium nitrate into ammonium ion, which is in aqueous solution, meaning in solution with water, forming ammonium ion again and nitrate ion. So the enthalpy, the change in enthalpy is 28.1 kilojoule. So it's positive, indicative that the reaction is endothermic. Whereas the formation of hydrogen chloride from elemental hydrogen and chlorine, the delta H is negative, indicative that the reaction is exothermic. Okay, we have three rules of thermochemistry. The first rule is that the magnitude of delta H is directly proportional to the amount of the reactant or product. Meaning, the greater the reactant is, the higher or greater would be the delta H. Okay, so we have tables for the heat of formation of substances. So we get values from these tables. So for example, we compute for the delta H or the change in enthalpy for the formation of 2 moles of hydrogen chloride. No? So we have this thermochemical equation. Hydrogen, 1 mole of hydrogen 1 mole of hydrogen gas plus 1 mole of chlorine gas forming 2 moles of hydrogen chloride gas. So this is equivalent to an enthalpy, change in enthalpy of 22 kilocalories. So we are asked for 1 mole. So this is simply ratio and proportion. So this 22 kilocalories is equivalent to 2 moles. So therefore, we just divide this by 2 to get the kilocalories involved in 1 mole of hydrogen chloride. So we have 11 kilocalories of enthalpy for 1 mole of hydrogen chloride. For letter B, we want delta H for 1.0 gram of chlorine. Take note that this thermochemical equation is in terms of number of moles. So we want to determine the number of moles of chlorine gas equivalent to 1 gram of chlorine gas. So we use the formula number of moles is equal to mass over molecular weight. So this is a review from your general chem. Although I also gave a PowerPoint presentation as well as a video on this. So the mass is 1 gram. So you divide 1 gram by the molecular weight. So 35.45 chlorine times 2. So 70.9 sa molecular weight. So 1 divided by this will be 0.014. That means 1 gram of chlorine is equivalent to 0.014 mole. However, that is just the number of moles of chlorine. We want the number of moles of HCl. So from the reaction, 2 moles of hydrogen chloride is equivalent to 1 mole of chlorine. So 0.014 mole is equivalent to 2 times that. So 0.028 mole. So 0.014 mole of chlorine from the 1 gram chlorine is equivalent to 0.028 mole of hydrogen chloride gas. And therefore, the delta H for 0.028 mole is simply this one. So the ratio and proportion. If 22 kilocalories is equivalent to 2 moles, how much calories is equivalent to 0.028 moles? So 22 kilocalories times 0.028 divided by 2. So you have 0.308. So this is in consonance with the rule number 1. The delta H is proportional to the amount. So 22 kilocalories is equivalent to 2 moles, whereas 0.308 kilocalories is equivalent to 0.028. So we have another example, no? So using a coffee cup calorimeter. So ice 24.6 grams is equivalent to 8.19 kilojoule. So phase change, no? Solid water, so ice into liquid water. So what is the delta H involved? Note that 24.6 gram is equivalent to 1.37 mole. And therefore, for 1 mole of ice, that is 1 times 8.19 by 1.37, that's 5.98. Again, in consonance with the rule. 24.6 grams, so that is 1.37 mole, is equivalent to 8.19 kilojoule, whereas 1 mole is equivalent to 5.98 kilojoule. Rule number 2, delta H for a reaction is equal in magnitude but opposite in direction to delta H for the reverse reaction, like in this example. From solid to liquid, we have 6 kilojoule. From liquid to solid, we also have 6 kilojoule, but the sign is opposite. Okay, so for example, we want to determine the delta H for the decomposition of 2 moles of water. From the thermochemical equation, 1 mole of water formed is equivalent to delta H of negative 285. So for the reverse reaction, but this time we have 2 moles, we multiply this by 2. So 285.8 times 2, but we get the opposite sign. Why do we get the opposite sign? From negative, it becomes positive because of rule number 2, because the reaction is reverse. Okay? So for the decomposition of 2 moles of water, delta H is 571 kilojoule. Rule number 3, the value of delta H is independent, no, of the steps, no, whether the reaction occurs in a single step or a series of steps, the value for delta H remains the same. So that is what we call the Hess Law. Okay? So for example here, so we want to calculate the delta H for the formation of carbon monoxide given these thermochemical equations. Okay, so given this thermochemical equation, for the formation of carbon dioxide, we have negative 393.5. This is from carbon and oxygen. Whereas for the formation of 2 moles of carbon dioxide from carbon monoxide plus oxygen, that delta H is negative 566. So we want this reaction. So that should be the final reaction. So how do we arrange our thermochemical equation? So we just copy the first equation and we just affix the same value for delta H. For the second equation, we need to reverse. No? We need to reverse. Why? So that we will be able to cancel out carbon dioxide. So why do we have 283? Because we only want 1 mole of carbon dioxide. In the given equation, there are 2 moles, so we divide 566 by 2 and then get the opposite sign. Why? Because the reaction will be reversed. The carbon dioxide now will be the reactant, and carbon monoxide and oxygen are the products. Why do we need to do that? Because we want this reaction where the carbon monoxide is the final product. Okay, so we simply add the equation. So we have carbon, and then carbon dioxide will cancel out. We have carbon from the left side and carbon from the right side, so they would cancel out. Then we have 1 mole of oxygen on the left side. We have 1/2 mole of oxygen on the right side. So we subtract this from this, so we have 1/2 mole. So look at the equations. We now have what we wanted in the first place. And what is the delta H, no? So delta H will simply be the sum of this, no? So we just copy delta H from the first equation, divide delta H from the second equation, and then get the opposite sign. So overall, we have a value of negative 110.5 kilojoule. Now, for enthalpies of formation, delta H which is delta H or heat of formation. So the standard molar enthalpy of formation, delta H sub OF. Okay, so we have the same formula. That's delta H of products minus reactant. Okay, so we have another table for standard enthalpies of formation. So for the change in enthalpy, so this is what I mentioned earlier. So the standard enthalpy change, is simply delta H of products. So delta H standard enthalpy of formation of products minus standard enthalpy of formation of reactants. So basically, you just have to identify which are the products and which are the reactants, which can be easily seen from the equation. Okay, so for example, calculate delta H or enthalpy change for the combustion of propane. So a combustion reaction always needs oxygen. So this equation tells us that carbon dioxide and hydrogen are the products, so here, and then propane and oxygen are the reactants, so here. We also need to affix the number of moles. So we have 3 delta H of carbon dioxide plus 4 delta H of water minus delta H of propane. Oxygen is 0 since it's element. And then you just do simple algebra. You will have delta H or enthalpy change for the reaction to be negative 2218.65 kilojoule. So it's very, very simple, no? So you just have to be very, very careful in affixing the values, from the tables. So this one, thermite reaction, okay? So you just do the same thing. Okay, so applying Hess Law. So this happened in series of steps, no? The series of steps, so you have HO1 and HO2 will be the same if the reaction happened in one step. Okay, so again, products minus reactants. What are the products? Iron, 2 iron, and aluminum oxide, 1 aluminum oxide. Reactants, aluminum, and then ferric oxide. Okay, so we just get these values from the table, no? So you look at these values from the table. Since iron is an element, so it's 0. And then, simple algebra. You have delta H to be this value, 2785.44 kilojoule. Okay? For enthalpies of formation of ions in solution, so practically we have the same principle. It's simply summation of products minus summation of the reactants. Only that you will have to look at the table for ions. So here we have standard enthalpies of formation of ions in aqueous solution. So when hydrochloric acid is added to a solution of sodium carbonate, carbon dioxide gas is formed. So here is the thermochemical equation. So what is delta H for this reaction? So you just define the equation. Delta H, okay, is equal to the summation of delta H of formation of products minus reactants. So you just identify the products and the reactants. So carbon dioxide is one of the products, as well as water, minus the summation of the reactants, which is hydrogen ion, 2, because there are 2 moles, and 1 mole of carbonate ion. And then, affixing the values from the table, so carbon dioxide here. Carbon dioxide from the previous table, we get here the ions, no? What are the ions? Carbonate ion, and hydrogen ion. So this is 0 because it's element. So carbonate is negative 677.1. So that's it. Just affix and then do a little algebra. And then you have final answer of negative 873 kilojoule. The reaction is exothermic. So if you touch the reaction vessel, you will notice that it is hot. Okay, so I'll give you, that's the end of the presentation. I'll give you some items to solve on your own as a practice. Okay.